gibt sowieso keine Anonymität mehr. Das ist sowieso.
Das wird ja das Ihnen zugedichtet.
Das sowieso. Okay, so then let's start with what I call theories of human decision making. And of course, this has also a lot to do with neuroscience, and it also has a lot to do with artificial intelligence, but we will see what we actually talk about in a second. That should work. Then let's have a look whether that works. Or we go into this mode. We go into this mode. So let me just switch something here. There we go. Still working? Yes. Good. So theories of human decision making, in a way, this should also give you a little bit of the background for the applied papers that you looked at in the winter term. I guess that's what I will do. That's very nice. So starting out, theories of human decision making, the way we study them relates fairly closely to what we call computational cognitive neuroscience, because for myself, cognition involves all processes from external, sometimes also internal, but usually or often external stimuli that are somehow presented to an observer, over perceiving this, doing something with it, memorizing things maybe, but then also importantly coming to a decision and acting. So that's cognition for me. That means the whole process from perception to action is cognition. If one looks at this in a model-based manner, then this is these days called computational cognitive neuroscience. There's a conference which is relatively novel. This conference is in Berlin. It's actually the Cognitive Computational Neuroscience conference. I like the term computational cognitive neuroscience more because I want to distance myself on purpose from the computational neuroscience field. What are the ingredients there? What are the main inputs? Or what is this based on? Of course, neuroscience is an important aspect. Psychology, or at least cognitive psychology. Economics, because economics, after all, developed a lot of these decision-making theories. Statistics, because everything is uncertain and things are based on limited data. Mathematics, because statistics is mathematics. And artificial intelligence, because a lot of the models that have been used to explain human decision-making have also influenced how artificial intelligence is designed, created. I mean, you all know the story of the perceptrons, this very early neural net. That is, of course, has origin in psychology. So this is what you should never forget, is that actually the whole AI machine learning stuff that originated in cognitive psychology. But then at one point, psychology didn't catch up and they went their way. And right now, actually, there's at least some people, for example, like myself, try to establish cross-links and collaborations. Why do I have this here? Just to give you an idea basically to say that computational cognitive neuroscience, neuroeconomics, decision neuroscience, that's all the same. Yeah? It's all one big thing. So what we want to talk about in some detail are the following, and we have to see how far we get, especially given that, of course, there will only be one kind of lecture style thing per week, and I think I should sit down. Sound is better. There will be only one lecture style thing per week, and the other will be your project presentations. So we will definitely talk about economic choice theories. This is essentially all of this, economic decision-making, value-based decision-making, neuroeconomics, where people from economy and neuroscientists get together, so and also psychologists and behavioral economics or microeconomics. This we have to talk about. This might actually, or I at least think this is also interested for those that are more interested in kind of Social Wirtschafts- und Organisationspsychologie, I think, because this is mainly talking about stuff from economics. Then we shall talk about perceptual choice theories. As I already mentioned, this will be mainly signal detection theory, maybe again, but maybe also for the first time, I don't know. And a little bit of sequential decision making, which you have seen. And if time permits, it's not July yet, I will also have some stuff on integrated choice frameworks, by which I mean POMDPs. Frameworks for studying decision making, the neuroscience of decision making, and for designing AI that are not kind of only doing this or only doing this. Yeah? So let's see whether we get there. Yeah, but we will start with economic choice theories, and these economic choice theories are. So we start with economic choice theories, and these. What we want to talk about here are first some historical development. So this basically follows the decision neuroscience book. Early choice theories, revealed preference theory, which is kind of interesting from an historical point of view and will give us certain aspects that we're interested in. And then we will focus on expected utility and prospect theory. So this leads me to your winter term. Do you have a paper that explicitly looked at prospect theory? You say you paper a little bit, or no?
Not prospect, especially.
But?
Well, we have prospect in health psychology, right? Message frame.
Prospect theory? So Allais paradox?
Which kind of paradox?
Not paradox, but well, you have to frame a message in a certain way to emphasize the risk or not.
Yeah, I think
or
this
primary or secondary prevention.
Yeah, this is something different.
Well, that was the thing with the gain or loss frame?
Yeah, but it's an application, it's not what they...
Yeah, it's somewhat related to that, but I think it doesn't hurt. So if was it built on expected utility theory? Did you go like there was first expected utility theory, then there was Kahneman and Tversky, and then there was prospect theory?
We started with Kahneman.
Okay, yeah, I think it makes sense to go over that in some detail. It's a very important, so it was for a long time, and still is in some way, a very important workhorse for a lot of decision neuroscience studies that use lotteries. Have you looked at these lotteries in this thing? Lotteries? Lotterien? Good. Okay, so it's fine. I think it will be more detailed than anything that you had before. I'm quite sure about that. And it is actually, it has been, so if you look into the decision neuroscience literature, there's the field of perceptual decision making, which is dominated by drift diffusion models, which you have heard about. And there's this other field that is dominated by economic choice theories and prospect theory, expected utility theory, which you now hear about. Good. The difference between those, and we will come back to that, is that these early choice theories and also revealed preference theory are deterministic choice theories. Essentially, that means if you choose option A, and option A gives you something, then you get that for sure. Probabilistic choice theories, then usually done in terms of lottery choices, work that you choose a lottery and multiple outcomes are possible, and these multiple outcomes have probabilities associated with them, so choices are uncertain. So that's the major part of this expected utility and prospect theory. So yeah, just that you know from the beginning, we will go over what that means once we are there. And we start with early choice theories and a little bit of history. So this
of course, so the history of neuroeconomics and decision neuroscience is a little bit that it's a merger between economical theory of how people make decisions, how people decide what to buy, what not to buy, that's then the economy branch, how this influences the economy. And neuroscience, especially then late 20th century, cognitive neuroscience, fMRI, putting people into the scanner and let them make choices between uncertain between different choice options that might have uncertain consequences. The neuroscience you know a little bit about because you did psychology, you had a little bit of biological psychology, you know a little bit what fMRI is. So I'm focusing here on the economic side of things, and this is kind of a starting point for economics. Of course, in economy, it was not the primary interest of what's going on in the brain, but of course in economics, you know that there are two kind of fields: macroeconomics, which looks at kind of the behavior of markets in a macro perspective, and then there's microeconomics, which looks at the choices and stuff of the individual decision makers. These are there now, but the whole thing started more from these kind of questions of early economics in the 18th century. So how are prices for goods determined in markets? And how are things like the exchange value, so how much you pay for something, the production costs, and the use value related. And very early theories then have this kind of, or one early suggestion is this labor theory of value, so that the exchange value, so the price of a good, is proportional to the production costs. So if something requires a lot of work to be generated, then this is fairly expensive and everybody will pay a fairly high price for that. If something is easy to create, this will not yield a high price and nobody is interested in paying a lot. So of course this history that I'm here presenting is fairly simplified. It's based on the neuroeconomics book, so it has gone through the filter of the neuroeconomics people, but nevertheless I'm telling it this way. That was the early idea, so that prices and how much people pay depends on just the production costs. And then one very important thing for what will then in expected utility and also prospect theory will show up as utility functions is what is known as the marginal revolution of the late 19th century, which was proposed by these, what do you call them now, old white men, who basically pointed out that that prices that people are willing to pay also have to do with the amount of their possessed good. The important thing is, in a way, of all of this, that the prices are not kind of an absolute thing that are just driven by the origin of a good, but they also depend on the state of the people who are paying for that. And this is the very basic example. So the idea is here on the x-axis, it's basically notated how much of a certain good is already possessed. The question then is how much are people willing to pay to increase by something, and the idea is if you have very little of something, then an increase by one
is worth more to you than if you have a lot of something. The good example, so this is from the book, it's with the water and so on, and one thinks about things, and it's getting a little bit tricky. I think the better example from a real life perspective is like students versus, so student income versus real people income. So if you have an income of 500 euros, getting an additional 100 euros actually matters to you. At least it mattered to me. Now, if you, like me, have an income of, no, I don't have a high income. Actually, you can look up my income on the internet. But if I would now be very rich because I'm a professor and get 10,000 euros a month, then it's like another 100, whatever. So I would not basically do a big effort for another 100 euros. So for example, I'm not motivated to take part in any of the experiments they run here because you get like 20 euros. So then it's like, wow, it's really not worth my time for 20 euros to do this because I have a reasonable income. For students, these extra 20 euros that you can get, of course, make a difference. And this is basically what this thing wants to say. And it changes a little bit the viewpoint from saying, okay, because there is this external good or this income, if you look in the reverse order, that is because intrinsically it has this value. It changes this viewpoint to something that is more personalized and looks at the personal utility of paying something or receiving something. So the only and major point here is that this idea of utility and this decrease if you have more of something, this originates from this marginal revolution. Of course, this shows the thing in terms of the total wealth. This is basically what I just explained in terms of the student versus professor, rich professor example. Now, if you really want to get rich, don't go into academia, because it's actually also not, and as you also know, it's also what people get paid is in no way related to what they actually do. So this is totally uncoupled if you think of how much people earn that doing finances compared to what people earn who work in the, let's say, the healthcare sector. It's completely uncoupled. There's no relation, and one shouldn't look for it. Good. So the main points so far have been that decision makers experience some form of utility. This term is just there, and the utility per unit good decreases as a function of its availability. One thing is also that also derives from this is that, or the basic idea is that decision makers maximize utility by their actions. So that's a very common assumption in everything, that actually people act in order to achieve something. And then, of course, the question is, what are they trying to achieve? And of course, you can have different things that you're trying to achieve, which can also be conflicting. In any case, the idea is one can describe that by some form of utility that decision makers derive from their actions. Yeah? So that was not really an overview about early choice theories. That was just highlighting that there was some that economics started a long time ago, has the idea that there are these utilities of human decision makers or other decision makers, for example, legal things, legal institutions, and that one might be able to describe that. Then a little bit later, so early 20th century, there was a little bit of a so this concept of utility is, of course, a latent concept, so you cannot directly observe a utility function of someone. The only thing that you can observe are the choices that they make.
Yeah. So, for example, for the student example, taking part in the experiments, I have no direct way of observing if I just if I don't try to explain to you what a utility function is, and you are supposed to write it down. But from just observing your behavior, I cannot directly observe your utility function, for example, for money. But what I can observe is whether you partake in these experiments where you get paid a little bit or you don't, and so on. And this was one of the points that was stressed, for example, by Pareto in the early 20th century, also in economics, that utility is latent or hidden, and what economists observe are choices and the prices that people are willing to pay. Yeah. So in a way, this is kind of, there has been this idea of a utility function, then people talked about that for 100 years and said, yeah, utility function, and get ever more complicated, and then somebody says, yeah, but you can, don't you realize you cannot really observe them? And then you get this shift in what people talk about. It's like with early 20th century statistics, when Fisher came along and said, well, we have to look at frequentist statistics, and let's not do this inverse probability, aka Bayes inference anymore. It's always what happens. After some time, a paradigm in science gets a little bit old, and then people say, let's do something new. And yeah, there was also that there may not always be a one-to-one mapping between the choices that people do and some utility function, and that specifically different, and this is the main point here, different utility functions that people have. Different utility functions can explain the same choices, or the other way around, the same choices can be explained by different utility functions. We will see an example for that in a second. So basically the point there of this revealed preference theory was that one should look at choice data. Yeah? And this is then, if you look at behavioral economics or psychology of decision making and so on, this is also what people say. Of course, these days we should look how people behave and the choices they make. And it was also a little bit against this armchair kind of economics where people think, okay, people should behave like that, and then they write articles about it without ever doing, without actually observing choice data. So kind of against that. And what this brought, and what will be important later on for expected utility and prospect theory is it brought this preference notation with these kind of curly larger than and smaller than signs. Yeah? So you see here this kind of little symbol, apples essentially larger than oranges. What this should mean is that there's a preference for apples over oranges. Yeah, there's a preference for oranges over grapes, and in a way, if the decision maker is consistent, they should also prefer apples over grapes. However, this consistency is not of interest right now. Right now, the only interest is that we have this symbol here, which looks like a curly greater than, and it is a typical symbol in the neuroeconomics literature for a preference. Yeah? Good. Before I can show you this example here, this shows an example for a utility function, actually for two utility functions that is consistent with two kinds of choice things. I have to tell you a little bit about how to write functions, because this will be a common topic for a lot of the following slides, so you need to be a little bit familiar with that. And I need to change my so of course you all know what functions are from school, and maybe, I don't know whether you saw in statistics again what functions are, but what you definitely have seen in school is something like this, right? Good. So the way that functions are usually formulated in standard math are as follows. Oops, that's not good. This doesn't happen now all the time. The way functions are formulated in standard math is as follows. So a function itself is some abstract rule, something. You can also call it a mapping. It's an abstract thing, and this abstract thing one often calls f, and this f is for function. What a function does is that it takes elements from its domain. This is a set of things, which is called the domain of the function, to a set of things, which is called the range of the function. The elements in the domain of the function are usually denoted, or are often denoted, for example, by x. This is now an element of the domain of the function, and these elements are mapped onto what is known as the value of a function, which is denoted by f of x. So I assume you have seen something like this f of x previously. So this is a very general notation. That's the domain of a function. That's a set of things. Often these are numbers, but they don't have to be numbers, as we will see in the example. The range are also often numbers. Again, don't have to be numbers. Can also be letters or other functions or whatever. And then the function, or let's do it like this, they have input values which are called x, and they are elements of the domain, and they have output values which are elements of the range. So concretely, to link this to what you've seen in school, to write this function, which you're of course very familiar with, so this is this function where you put in numbers, so x's, and you square them, and then you get something like this. I don't want to touch on the screen, that's why it looks a little bit weird, but you get this parabol x square. To write this in this notation would then mean that you call something f, you specify its range, for which you, for example, take the real numbers, which are just all numbers here on the x-axis, and these real numbers get mapped onto real numbers, which are all numbers on the y-axis. And you specify things as follows: x, which is a real number because it's in the domain, gets mapped onto the value of the function f at this location, which is an element of the real numbers, so it's a number, and you define this, and that's then the important thing, you define this as this little computation, namely as x squared. Why this extra effort of defining a function? Because in a way you could say, yeah, but it was perfectly fine in school to work with these kind of things. Yes, but of course in general you might not only always look at functions of single elements, but of multiple elements. So then you can specify, for example, higher dimensional input spaces, vectors, higher dimensional output spaces. You can be even more creative and define input and output as function spaces, and so on. So this is just a very useful general notation for functions that will be applied also in the slides to come. And I will give you a first example of this notation in a second. Other questions about this? This is just function notation in math. Basically, yeah. So another example that you are familiar from from statistics is, for example, simple linear regression, where you have where you have x as your input argument, you have two parameters, a and b, and you have this functional form of your model for data. Yeah? Of course, this can be generalized to multiple linear regression or the GLN or neural networks. Good, so that's function notation, and with this function notation I now want to show you more about this ordinal revolution. So the point here is that different utility functions can lead to the same choices. And the example is as follows. So here you have one utility function. Wait, let me get my pointer. Here you have one utility function which I call u1. And this utility function maps the elements of its domain, namely A, O, and G, for apples, oranges, and grapes, onto the real numbers. It's a utility function, so it's a mathematical object. It's a model. Yeah? It's a mathematical model. It maps them onto the real numbers. It takes as inputs x, which is one of these, so apples, oranges, or grapes, and as outputs it assumes a value for its input, for its specific input. And here I define the values of this function not by a little computation, but directly. So this utility function for apples, it should say or give out as output 3. For oranges, it should give 2, and for grapes, it should give 1. So that means that the utility for apples is larger than for oranges is larger than grapes, and for apples is also larger than grapes. So if now a decision maker follows this utility function, they should prefer apples over oranges, oranges over grapes, and oranges over granges, apples over grapes. Yeah, that's one utility function. And the point of the revealed preference theory / ordinal revolution is that you can observe exactly the same pattern for a different utility function. So here I have the utility function u2, again defined on the domain A, O, G, mapping to the real numbers, and here defined as essentially the square of this function. So for apples, this yields 3 to the power of 2, for oranges 2 to the power of 2, and for grapes 1 to the power of 2. Again, the choices would be consistent. The choices that follow from this utility function would prefer apples over oranges, oranges over grapes, and apples over grapes. The point is here a little bit in terms of if you think from a modeling psychology, cognitive psychology perspective, is if you observe these kind of choices, you cannot really differentiate between these models for the utility functions of the decision maker, yeah, because both are consistent. Both utility functions are consistent with these choices. So this also led a little bit to what is then called ordinal revolution, that it's more about the ordering of choices, and like this is what I think is best, this is what I think is second best, this is what I think is third best, over assigning absolute numbers like utility of 100, utility of 90, utility of 80 to things, hence ordinal revolution. The main point for us later on when we talk about expected utility and prospect theory will actually be this symbol here. So you don't really need that much. Of course, there are many more possibilities for utility functions. Yeah, and this is what I just said. This is what Pareto pushed. Now then, based on this, what actually happened in the first half of the 20th century is that based on these concepts, different people try to kind of link this idea of there's a utility function and there are these preferences, and trying to make a coherent mathematical framework. Yeah. So the thing is that all mathematical frameworks, they don't fall from the sky and were given to Moses on the Mount Sinai, and then they got into your school book or your statistic book, but they were developed by humans based on certain motivations, and these kind of mathematical framework developments involving utility functions and involving choices were done in the first half of the 20th century by some people. So Samuelson contributed to that and developed at first what then in neuroeconomics is called always called axiomatic system. So what is this about? So essentially it's about the idea that if you assume certain truths, so certain axioms, then something follows. That's typical math. So in math you assume certain things and say, I assume this, this and that, and then it follows that this happens. Of course you can say, yeah, what happens if I don't make these assumptions? And then the mathematicians would say, well, then there's no guarantee that this follows. Yeah? And then the whole thing doesn't make sense. So axiomatic systems are always based on some axioms which assume to hold, that then have certain consequences. And the nice thing about axiomatic systems is to basically spell out what the necessary and sufficient conditions for certain mathematical theorems or theorems in general are. Yeah? So there is a lot of value in this to develop axiomatic systems and then prove that under these axioms certain things hold. What these axiomatic systems don't say, and this is what always drove me nuts when I worked at MPI, is that anybody claims that these axioms actually hold, for example, for human decision makers. This is not the claim at all. These are just logical relationships. If you assume this and this, if you assume A, B, and C, then X, Y, Z follows. It doesn't mean that nobody says that A, B, and C hold for human decision makers. Yeah, and this is very important in this context, because this is often, from my experience at least, confused. That basically then behavioral economists or also psychologists of decision making say, yeah, but this is not true for humans. Yeah, but that was also not why they talked about this in the first place. So let's look what Samuelson got up to. So he developed a necessary condition for a utility function maximizing decision maker. So basically, this Samuelson weak axiom of real preference sounds like sounds fairly fancy. What it says is, if for a certain decision maker A is preferred over B, and the decision maker is consistently maximizing a constant utility function, then it cannot occur that the decision maker prefers B over A. Yeah, so this is a smaller than sign with some curly, so it means the reverse preference. It's not, I mean, mathematically it's interesting. It's not something, of course, something where you then immediately, so first of all, you of course, you know from yourself that you sometimes prefer A over B, and at other times you might prefer B over A. So it says nothing essentially about human psychology or decision making. It's a mathematical statement based on the idea of utility functions and preference, but it gives you an idea of this. We will talk in some length about the axioms of expected utility. So this is kind of all leading up to that and trying to make you familiar with these kind of things. Reversely, if for a decision maker A larger than B on some choices and A not preferred over B on other choices, then the decision maker cannot be maximizing a unique utility function. Makes sense, but again, from the perspective of modeling human decision making, of course, by no means is there an assumption that humans throughout their lives always maximize some utility function. So my take on this is essentially, usually we assume also in our experiments, we assume that people are doing something, so that they're maximizing something. But this might well be of going home as fast as possible and minimizing the cognitive effort. But they're doing something, which doesn't necessarily mean that they want to perform best on a certain task and get all the rewards. They have some motivation, and this they are following. And this you might be able to describe by a utility function, but of course these utility functions can change in different contexts. This kind of revealed preference theory then went on a little bit, going on from the Samuelson work, which actually is much more than this. The Samuelson work is actually a dynamic systems approach to decision making and so on. So this is all left swept under the rug here, focusing on the axioms of real preferences. The work by Huthacker, I think is Dutch. Then is again mathematical work that shows if the transitivity of preferences, meaning that if you prefer A over B and B over C, and from this it follows that you also prefer A over C, if this holds for a decision maker, then there's at least one utility function that can account for the decision maker choices. So that's an existence proof in math, which is usually not that simple. Intuitively, it doesn't. It ensures the mathematical existence of a unique utility function. Usually these kind of existence proof, they don't say how this utility function looks. So it doesn't, if you're trying to model now human utility function, it doesn't really give you something to work with. It just is a proof of existence based on the transitivity of preferences. And this transitivity of preferences we will come back to when we talk about expected utility theory, which is the main point here in this lecture. So this also shows, and this is the main point for this revealed preference theory, that ordinal utility and revealed preferences, you can actually show that they are formally equivalent. So remember, Pareto said we should focus on the ordinal stuff. So is that the first, this the second? I prefer this over that. I can only observe the choices. This work then shows on the mathematical side, if you have essentially a unique utility function, you observe this transitivity of preferences. If you observe the transitivity of preferences, then there's a unique utility function. So this is then essentially some kind of summary of what all these things say. And there's actually a nice article by Varian from 2006 that summarizes this history of revealed preference theory and its origins in early economic choice theories. Essentially, you can, and this is what behavioral economics economists prefer, you can ask people about the preferences. So do you prefer apple over bananas? And then they say yes. Grapes over strawberries, this. And if they are never inconsistent in their choices, so here, can we say something? No, but if there would be something like they also prefer bananas over kiwis, that would mean they should prefer apples over kiwis or be indifferent about them. Then you can construct a function that has on its x-axis the thing that you're interested in here, fruits, and on the y-axis it has the personal utility. No? So that's essentially the outcome of this revealed preference theory together with utility theory. And this is all to actually set the stage for expected utility. Before this starts, let me highlight what I think is positive about everything up to now. So it's positive that there's some mathematical development, so it's tried to be formal and specific and detailed about how humans make decisions, and also especially this revealed preference theory puts an emphasis on an interaction of empirical evidence and formal development. So the beginning of revealed preferences was against, like I said, this armchair economics where people just start widely speculating about what utility functions humans could have without observing actual choice behavior. And this is what revealed preference theory points out. One should look at that. It has, in a way, some negative or whatever. So what I don't think is that awesome about this whole thing is this whole insight that this utility cannot be directly observed, and this is a latent concept. This is always the case. Every scientific explanation for observable phenomena is always latent. That's not at least from my early 21st century view, that's not something that is too surprising. My example is always, of course, with fMRI, you always have people saying, yeah, but this is not really neural activity because this is Boole signal and this has to do with blood flow and so on. Yes, that's true. Or people say EEG, well, that's not really neural activity because it's on the scalp. That's also true. But if somebody sticks an electrode somewhere, what they observe in the brain, what they observe is the current in their electrode. And then they have a model of how neurons might create that. So it's the same thing. It's just, you need different latent constructs and rely on different latent constructs to explain observable data. So that's not really a new insight. What is missing from this whole thing is that, of course, if you say people are should never be inconsistent people in these kind of revealed preference tasks, do you prefer this over that or that over that? Of course, they sometimes can make an error, right? So they, and this is a non-probabilistic and noise-free theory so far. So it's missing something, and this is what I already mentioned, that these axiomatic theories, of which expected utility and prospect theory, especially expected utility will also be one, this is just a mathematical framework that says if you assume this and this and that, then this holds. It's not a scientific theory in the sense that it's a model for something. Yeah, and this is. Yeah, it's also in the neuroeconomics books. Sometimes people just confuse that, and then they write and say, basically, for example, about the Neumann-Morgenstern axioms that we will come to say, but that's not true. Then come up with a new model and study its implications. That's then the point. Good, and we had that. So. This is essentially what we can take from these first excursion into, or unsere erste Wanderung. Our erste Wanderung into economic choice theory. What we can take from that is that in these early choice theories, the outcomes of decisions are considered as deterministic. If I choose apple over orange, I get the apple. There is no there's no uncertainty with respect to the outcome, then the idea is that decision makers and humans maximize something that one can refer to as utility. We've also seen that utility and preferences are fairly closely related. So if I prefer this over this and this over that, and from this follows that I prefer this over that, then there is, one can express that in a utility function. One important thing that will come up throughout is that utility functions can be concave. What concave really means, we will talk about, but this is this outcome of this marginal revolution, that essentially if you have already a lot of something, then an additional thing doesn't give you more. This is why often for a utility function, the log function is being used, as we will see later on. And that preferences, and that, that there's this notation in decision theories that uses these curly larger than signs. So that is, and the mathematization and axiomatization happen. Let's see. So that's what I wanted to say about these early choice theories. And now, let me have a look at the time. No, we don't need them. Okay, so we have 15 more minutes. So ideally, you would now have some questions, and we discuss these questions, because I don't think it's really much worth to start with the expected utility theory, because we won't get any far. So do you have questions about these things that we've that I told you about now? Have you heard any of this before? So who has heard about the marginal revolution? Who has heard about a utility function? Yeah, so in which context did you hear about utility function?
I think in a summer during my bachelor studies, I actually wondered what kind of background do the people who came up with these theories have? So what did they study? Were they mathematicians?
Yeah, I think actually usually, so some of them, I think Neumann Morgenstern, when we talk about expected utility theory, they might have been mathematicians, but it's a strong interaction. So in economics, so usually what happens is that in some domain, people start coming up with things and try to be more specific, and then some mathematicians look at what these people have done and say, oh my God, and write it up better. That's the common thing. So, for example, expected utility, which goes back to a publication by von Neumann Morgenstern in the 50s, they essentially assessed what is there, what kind of models people have developed, and then try to clarify certain things and worked as mathematicians. But I don't know whether anyone knows anyone who studies economics. Also, if you study economics, of course, you are exposed to a certain degree of math. Especially talking about functions is a big thing in economics. Does anyone know somebody who studies economics? No.
Friends of mine.
Yeah. So they do some math. Yeah? So in a way, they do math the way you do statistics. So it's not kind of the math, but it's kind of this applied stuff. But they have it. And of course, in terms of the motivation of these people, so the early economics and most of economics these days is, of course, interested in policy making. Yeah, so they try to figure out how things work, to have an idea of telling policymakers, politicians, what they can do to make something better. So to, I don't know, increase welfare of a lot of people, something like that. So that's usually an interest of economists to look into these things. But a lot of economists are also completely not interested in what happens at the individual level. And they actually, this kind of microeconomics and behavioral economics and also new economics, a lot of economists say that's completely irrelevant. What we are interested in is aggregate data, not of the individual, but what big groups of people do, and this what individuals do. This all averages out, so we don't have to look at it. And this is actually so behavioral economics. So doing these kind of economics experiments and kind of psychology decision-making experiments is. Some people like it in economics, and other people hate it.
I think what's also interesting, if you are more interested, like Adam Smith, he had this idea about people want to maximize their own things in the first place before they were like, or in the development of like economics. But he also had the second book, like Theory of Moral Sentiments, where he included like the more closer look on people behavior, and that's like as an impatient spectator, and people have empathy and sympathy for each other, which is also interesting to read. I had another question, like this concept of utility. That's like the basic theory we talk about. The axioms are not theory at all, but utility is like this idea that is so far not proven or not observed.
Well, it's in a way, it's just a latent construct. So it's a scientific construct.
Not a theory. Not a theory.
Oh, that's for me the same. So for me, utility functions as mathematical functions are mathematical models that can be used to explain behavior. So, and in this sense, you can, in mathematical contexts, you can say, okay, there exists a unique utility function for a decision maker that behaves like that. However, that's kind of a mathematical statement, because you can, of course, model human behavior in all sorts of ways. And sometimes they might behave inconsistent, and then you, from my perspective, you would still assume that they have a utility function, but sometimes make errors, which of course in math wouldn't happen. So essentially, it depends on the model class that you then use. So I think because these are latent constructs, it's not really possible in kind of empirical research to prove their existence.
It wouldn't be latent. It wouldn't be latent if it could be observed.
Yeah, exactly. And it's then in the end, you can, of course, in science, you can never really prove anything. You can just have a lot of evidence that's pointing towards something, and then you might believe it more. Other questions? No. Good. Then I think we stop here, and you use the remaining 10 minutes to think about your project. And then next time we will talk about expected utility. And again, this intro today, so today was essentially the intro to talk about expected utility, and which is, together with prospect theory, the leading theory about in behavioral economics today. Yeah? Good. Then have a good Easter break, and I'll see you in 2 weeks.